This report is on the Fukushima Dai-ichi nuclear accident. This research paper presentation is based on the research paper written by Frank Turner, David Giuliano, and Keith Woods. On March 11, 2011, an earthquake struck east of Tohoku. This is the fourth largest earthquake ever recorded, and it resulted in a major tsunami. The tsunami collided with Japan and caused billions of dollars to Japan and its infrastructure. One of the major problems that occurred was at the Fukushima Dai-ichi nuclear complex. The tsunami caused major damage to 4 out of the 6 reactor plants located at Fukushima Dai-ichi. We are going to analyze the problems that occurred at the Fukushima Dai-ichi nuclear plants and the actions taken by operators to combat this nuclear accident. As you can see here, the earthquake epicenter was off the east coast of Japan. The resulting tsunami killed at least 15,700 people, 5,300 people were injured, and 4,650 people went missing. The objectives for this PowerPoint presentation: we're going to discuss the status of Fukushima Dai-ichi reactor plants, units 1 through 6, before the earthquake hit. We're also going to discuss the events that occurred for units 1 through 6 after the tsunami hit the Fukushima Dai-ichi nuclear complex. We're also going to state the status of the spent fuel pools after the tsunami hit, including both the common spent fuel pools for units 1 through 6, and dry cask storage. The references that I used for this presentation were the American Nuclear Society Committee report on Fukushima Dai-ichi, the Institute of Nuclear Power Operations special report on the nuclear accident at the Fukushima Dai-ichi nuclear power station, and the United States Nuclear Regulatory Commission Japan Lessons Learned. The following slide shows the status of units 1 through 6 before the earthquake hit Japan. Units 1 through 3 were operating before the earthquake hit. Units 4 through 6 were in a cold shutdown condition and outage. The cold shutdown condition is when reactor pressure vessel water temperature is less than 100 degrees Celsius. Unit 4 was also defueled at the time, and the fuel is being stored in the spent fuel pool for Unit 4. Units 5 and 6's fuel was located in the reactor core. At 1537, the water generated by the tsunamis began to flood the turbine basement. As the turbine basement flooded, it began to submerge the AC/DC electrical distribution systems and the diesel generators. By 1550, all of the on-site power was lost. At this point, there was no method of decay removal or injection of water into the core. At 1636, the operators lost the ability to determine the reactor pressure vessel water level. Operators also lined up core injection at this point using a diesel-driven fire pump. Reactor pressure had to be below 100 pounds force per square inch gauge to use this method of core injection. At 1818, control room operators placed the isolation condenser on service remotely. At 1825, the control room operators removed the isolation condenser from service. No reason was determined for why it was removed. At 2119, core indication was restored. Water level was 8 inches above the top of active fuel. At 1:48 on March 12th, the diesel-driven fire pump stopped operating. At 2:30, the containment pressure began to increase to 2 times its design pressure. At 5:44, the fire engine began injecting fresh water to the core. However, reactor pressure was only slightly below the fire engine pump discharge pressure, so not a lot of water was actually being added. Another problem with using the fresh water was that there was only a limited supply. Every time the tank had to be filled, core injection was stopped in order to fill up the freshwater tank, which only had one connection. At 14:30, the primary containment was vented when the rupture disc opened. 1536, a hydrogen explosion occurred in the secondary containment and resulted in severe damage. The hydrogen was generated by the high temperature interaction between zirconium and steam. At 1904, seawater was added to the core by the fire engine, because the fire protection tank ran out of water. Boron was also added to attenuate neutrons because there were concerns of criticality. On March 20th, the off-site power was finally restored to. The following picture shows the damage to the Fukushima Dai-ichi Unit 1 site. At 1541, the tsunami caused flooding in the turbine basement. As the turbine basement began flooding, it emerged the diesel generators and the electrical distribution system. One of the emergency diesel generators was air-cooled and was not submerged. However, the distribution system for it was submerged. At 1636, the reactor pressure vessel water level indication was lost. At 2150, the reactor water level indication was restored. The water level was 134 inches above the top of active fuel. On March 13th, the vent lineup was complete, but containment pressure was not high enough to open. At 1325 on March 14th, the operators determined that the RCIC failed because reactor water level was lowering. At 1630, water level decreased below the top of active fuel. A fire engine was lined up, but reactor pressure was not low enough at this time to add water. At 1954, seawater was injected into the core. Boron was also added at this time. On March 15th, at 0600, an explosion occurred at Unit 2. A breach of containment occurred and caused the containment to depressurize. On March 20th, off-site power was restored to Unit 2. The picture here shows you where the steam cloud is coming out of Unit 2 where they had the breach of containment. At 1538, the tsunami caused flooding in the turbine basement of Unit 3. This caused the electrical distribution system to be flooded and the emergency diesel generators to also be flooded. At 1603, the RCIC system was restarted to maintain water level. On March 12th, at 1136, the RCIC system shut down unexpectedly and would not restart. At 1235, the high-pressure core injection system started on a low water level. The high-pressure core injection system uses steam from the reactor to operate and has about 7 times the capacity of the reactor cooling isolation system. This caused reactor pressure to lower because of the turbine drawing steam. At 2036, reactor core water level indication was lost. On March 13th, at 2:42, the high-pressure core injection system tripped. The batteries for the system were determined to be exhausted. At 4:15, the reactor core was uncovered because all methods of makeup water injection into the core were lost. At 8:41, the containment vent lineup was complete and the operators began to vent the containment. At 1312, seawater was added to the core. On March 14th, at 1101, a hydrogen explosion occurred, which damaged the containment. The off-site power was eventually restored on March 22nd. The following slide shows you the damage to the Unit 3 containment by the hydrogen explosion. Fukushima Dai-ichi Unit 4. So on March 14th, a hydrogen explosion occurred in Unit 4. This was a surprise, especially because the reactor was defueled and there was not a lot of decay in the fuel stored in the spent fuel pool. This caused a scare because the operators thought that the spent fuel pool might be becoming uncovered. This diverted a lot of attention away from stabilizing the other. The theory on why the hydrogen explosion occurred at Unit 4 was that there was a backflow of hydrogen from Unit 3 to Unit 4. This slide shows the vent lineup for Unit 3 and Unit 4. As you can see, the two exhaust vent paths are connected. No backflow dampers were installed in the exhaust piping either. Since there was no power to the exhaust fans, the hydrogen backed up in the Unit 4 and caused the hydrogen explosion. As you can see here, this slide shows you the damage that occurred because of the hydrogen explosion in Unit 4. Fukushima Dai-ichi Units 5 and 6. So, at 1541, tsunami caused loss of power to Fukushima Dai-ichi Units 5 and 6. Luckily, Unit 5 and 6 are located at higher elevation than Units 1 through 4. Unit 6 had an air-cooled emergency diesel generator that was not damaged by the earthquake. This diesel generator was able to supply power to both Units 5 and 6. Both of these reactors were able to be depressurized and decay heat removed, and both units achieved the cold shutdown condition by March 20th. The first of the spent fuel pools we're going to talk about is the common spent fuel pool. Approximately 60% of all the fuel at the Fukushima Dai-ichi site was stored here. At the time of the accident, the pool was about 80% full. All of the fuel located in the common spent fuel pool is usually stored in their respective unit spent fuel pools for 19 months or longer before being moved to the common spent fuel pool. This resulted in a lower decay generation by those spent fuel rods. Cooling can also be lost to the common spent fuel pool for 30 days before damage will actually occur. The individual spent fuel pools. The cooling was lost to the common spent fuel pool and individual spent fuel pools when offsite power is lost. Power is not immediately restored to cooling for spent fuel pools after the power was lost either. Units 1, 3, and 4's hydrogen explosions caused their individual spent fuel pools to be exposed to atmosphere. Unit's 2 spent fuel pool was exposed to atmosphere because of the blowout panel being lost. After the hydrogen explosions, there were a lot of concerns that water inventory was lost to the spent fuel pools. Fire engines and water cannons were brought in to attempt to keep the fuel covered, but they could not reach the top of the buildings. Helicopters also attempted to drop water on top of the spent fuel pools, but the radiation levels were too high to maintain a low altitude, so this was unsuccessful. Concrete trucks were eventually brought in to pump water into the spent fuel pools. None of the spent fuel pools were ever uncovered. This slide shows you where the spent fuel pools are located for units 1 through 4. It also shows you the area of the explosion for units 1 and 3 at Fukushima Dai-ichi. The picture on the left shows you the design of the dry cast storage canisters. The picture on the right shows you how the canisters are stored. At Fukushima Dai-ichi, there are 9 dry cast storage canisters. In those 9 dry cast storage canisters, there were 408 fuel assemblies. Damage occurred to the building after the tsunami hit, but no damage occurred to these dry cast storage canisters. So today we discussed the status of Fukushima Dai-ichi reactor plants, units 1 through 6 before the earthquake hit. We discussed the events that occurred for units 1 through 6 after the tsunami hit the Fukushima Dai-ichi nuclear complex, and we stated the status of the spent fuel pools after the tsunami hit, including both the common spent fuel pool, spent fuel pools for units 1 through 6, and dry cast storage.